Right, so the next talk is by Svetlana Pastukhova. It's joint work with Vasily Zhikov, and it's about homogenization in quasi-periodic situations, quasi-periodic operators.
First of all, I thank organizers for inviting me here, this remarkable place, and for opportunity to make a report to popularize our results, joined with Vasily Zhikov. He represents, he's Vasily, not Vladimir, but he's from...
No, I know.
But he presents, first of all, Vladimir State University and also Moscow State University. And I am from some technical Moscow University. So, before I proceed to the main results, I will briefly make some preliminaries concerning the general homogenization and operator estimates. As in previous hour, we shall discuss homogenization, but not highly contrast, moderate contrast. So we have here some inhomogeneous equation depending on small parameter, but inhomogeneity does not abstract to solution to have some boundedness and compactness properties, so there holds convergence in some sense, and the main aim in homogenization to pass to the limit in this equation to find the so-called homogenized equation to which the limit function satisfies. In the most simple example, we have operator, inhomogeneous operator A epsilon of this type, divergent type elliptic equation of the second order, where inhomogeneity is in highly oscillating. So the matrix of coefficients. Coefficient matrix is obtained from one periodic matrix A of 1, which is supposed to be measurable, symmetric, one periodic. So periodicity cell is a unit cube, and brackets will denote the mean value over the cell of periodicity throughout all my talking. And in this simple example, the limit equation is of the same structure. Here is moderate contrast homogenization, so homogenization does not change the structure, but limit equation is much simpler. It is the equation with constant coefficients, and the matrix A0 is calculated through the well-known procedure. You should consider so-called cell problem. It is the problem here. It is the equation on the unit cube with periodic equation boundary with periodic boundary conditions. So this problem is initial one and limit one are well posed, and when you take the mean value of the flux of this equation, you obtain one of the column in the homogenized matrix. I must say that here vector Ej is one of the vectors from canonical basis from Rg. Here we have strong convergence in L2, and it can be named as, called as strong resolvent convergence for operators A epsilon. Yes?
Is it, the last line, is it just equation where we find n, j from?
Yes, with periodic boundary condition on the boundary of unit cube. It is of the same divergent type with elliptic matrix, but here the right side function may be written not in usual form. This part forms usual right side function. So we have here strong resolvent convergence of operator A epsilon to limit operator A. But in this problem, actually we have more strong operator convergence. It is uniform resolvent convergence. It means that in operator norm from L2 to L2, the difference of resolvents of initial operator and the limit operator converge to zero. This result is not very difficult to derive from strong resolvent convergence. And these results which I have just now told you were well known maybe more than 30 years ago. But last decades it was proved that the rate of convergence in this operator norm is of order epsilon. And such type estimates are called operator type estimates in homogenization. In more simple form, in terms of solutions of the initial problem and the limit problem, this operator type result can be formulated in the form of this estimate, when majoranta in right side function is of the form of the product. Here is L2 norm of the right side function, epsilon in power 1, and constant which depends only on dimension and lambda. U is usually called in homogenization as zero approximation or L2 approximation. Here I have explained why it is so. And if you want to approximate U epsilon together with its gradient or in the norm of Sobolev space, you should take the so-called first approximation, which is the sum of the zero approximation and corrected term, which is calculated with the help of the solutions of the cell problem. N is the vector function which is formed from ng, which I showed you previously. And for the difference of U epsilon and this function V epsilon, we have the following also operator type estimate, because here in the right side function we have the product of L2 norm of F, epsilon, and constant C, which depends on the dimension and ellipticity constant of matrix A. We can consider equation which was shown previously as a more complicated equation. For example, equation of elasticity theory. Then operator A epsilon is vector operator here. It acts on the vector function. In elasticity theory, U is displacement, and A or epsilon is not the matrix but the tensor, elasticity tensor of fourth order, which can be considered as an operator acting in the space of matrix. Here matrix will be the gradient of the vector function. So we can try to obtain operator type estimate for this class of operators also. But in this case, there will be no any problems. There will not be any problems with L2 estimate. Everything is defined correctly. But if you consider the first approximation, you, in the case of elasticity theory problem, n will not be function from L infinity. So even corrector form is not the element of L2, and we want that this function should be the element of Sobolev space. So for equation of more complicated time, there are a lot of complications, and we should modify the concept of the first approximation and the form of the H1 estimates of the operator type. So I have some review on homogenization and operator type estimates. And I must say that the interest to this topic arose beginning with works papers of Birman and Suslina. Tatiana Sanna Suslina participates in this conference, and maybe you have listened to her report. Maybe it was devoted also to this topic. And after a little bit later, Zhikov and his school also turned to this topic, and during 15 years there were proved a lot of results. They concern equations of different type, a broad class of vector equation, degenerate equation, even non-linear equation. We turn to not only to periodic setting, but also to locally periodic, multi-scale settings. Here, matrix, non-homogeneous matrix A epsilon X is obtained from the matrix A of X and Y, which is one periodic in Y. And so in this definition, we have a matrix which has slow variable X and fast variable X divided on epsilon. In multi-scale case, we have matrix A, which is periodic in variable Z and Y, and we have, for example, this replacement of these periodic variables with also with both fast variables, but they oscillate with a small period which are of different order. It is here essential that orders of smallness should be divided. But recently we have noticed that our technique, which starts from the first paper of Zhikov, can be extended to quasi-periodic setting. So I come to the main part of my talk. I remind you what is a quasi-periodic function. Quasi-periodic function is a function which admits the following representation. You have one periodic matrix of Z from Rm, which is continuous with periodicity cell m-dimensional unit cube. You have also the family of d-dimensional vectors omega 1, omega m, which are fixed and rationally independent. That means that the following relation holds. You have linear combinations of vectors omega g. We will call them frequency vectors. And the coefficients in these linear combinations are taken from integer numbers. This is the definition of quasi-periodic function, and throughout my talking we will consider the family of frequency vectors which are fixed, one and the same. We will not change it if we will speak about the quasi-periodic function in RD. But now I give you some simple example how quasi-periodic function can be imagined. You take function B capital. Always we shall call the periodic function which generates quasi-periodic function as the subset of the quasi-periodic function. So we have here subset which is defined in the plane, and we restrict this periodic function on the line with angle coefficient omega, which is irrational number. So if we identify the points in the plane in such a fashion that they are the same if they are obtained with integer shifting, then we can depict the image of our line in the framework of unit cube. And in this unit cube we have also identified opposite sides. So our line now represents on this quadrate, which can be called as torus, as some winding. And because of the irrationality of this number, this winding fills up the quadrate everywhere densely, and so it's quite natural to have such property for the function restricted on this line or on this winding. The average over the line or over the winding is the same as the average of the periodic subset over the cell of periodicity. In general case, the condition C1, which will be called simply independence condition, we have the coincidence of two averages. Average of the quasi-periodic function, which is defined as the limit of integral mean over the shrinking, the expanding family of cubes. And another average is the mean value of periodic function over the cell of periodicity. This relation is some simple variant of fundamental Bergov ergodic theorem. In our consideration, we need also additional condition for the family of frequency vectors. It is called simply frequency condition. It means that this vector linear combination of frequency vectors with integer coefficients can degenerate, can be small, but it cannot be small arbitrary. The degeneracy of this vector is of power-like nature. So, more strictly, there exist two constants, C0 and tau, positive, such that the following condition is fulfilled for every integer vector k. Now we turn to the divergent elliptic equation, and they define the quasi-periodic highly oscillating matrix. We take quasi-periodic, now I will begin with periodic matrix A capital Z, which is defined in Rm. It is continuous, symmetric, one periodic, and it satisfies the usual ellipticity conditions with the ellipticity constant lambda. Then, as it was explained previously, substituting instead of variables z, g, scalar products of frequency vectors and d-dimensional y, we obtain quasi-periodic matrix A small of y. And after replacement of quasi-periodic variable with fast variable x divided on epsilon, we have this highly oscillating quasi-periodic matrix A of epsilon. Further, we consider the equation which was demonstrated previously in periodic setting. But here, now we assume that matrix A of epsilon is, as I have explained, highly oscillating quasi-periodic. And in this case, it was long ago proved by Sergei Mikhailovich Kozlov and also by Sergei Kozlov, the result which is quite common for homogenization. There is strong convergence to the function which is the solution of the limit problem, and the homogenized matrix is calculated through well-known procedure. Vasil Vasilievich Zhikov also studied problems with almost periodic coefficients and quasi-periodic coefficients, elliptic, different parabolic equations, stabilization, homogenization, and now we want to supplement these old results with some new ones, which are the operator type estimates for the equation of the type 1. And we assume the conditions C1 and C2, independence condition and frequency condition, and also we assume that matrix A of Z is sufficiently regular. You see that in periodic setting it was sufficient to consider measurable matrix, but here we have substitution instead of variables zg of some scalar products, and to obtain matrix A of epsilon to be measurable, we should demand continuity and maybe some more properties will be necessary. Here we have so-called cell problem, number 3. Quasi-periodic equation as in periodic set but I will explain a little bit later that this cell problem, so-called cell problem, is much more complicated, is not so evident as in periodic setting. The homogenized matrix can be defined through this relation, and we can define as previously the so-called first approximation, V of epsilon, as the sum of zero approximation and some corrector. We will have assumptions on the matrix A be such that this factor will be bounded, so there will be no any complication with the property V epsilon belongs to the space H1. So in this, under this condition, we have proved the following estimate. It is operator type estimate. Here constant C depends on the condition C2, depends on two constants C0 and tau, and of matrix A capital Z. I have mentioned that here the so-called cell problem is rather non-trivial, so I will explain this now. The cell problem is the particular case of the equation 0. And here we have matrix and the right side function, quasi-periodic. The condition, frequency condition is satisfied, so we can state that this equation has a solution which is regular, which can be arbitrary regular if the right side function is arbitrary regular. Moreover, the following estimates for the periodic subsets of the quasi-periodic function n holds. It is an estimate which usually is called hypoelliptic estimate. In periodic setting, we have here norm with exponent c plus 1, but here we have the loss of ellipticity, which depends on the exponent tau from frequency equations. And maybe I will comment how we prove this lemma. There are a sequence of arguments which show that to obtain the solution of the equation 0, you should find the function which satisfies the equation in the sense of average of almost periodic function here brackets denote the average of quasi-periodic function. And due to independence condition, this problem can be transformed to the problem of finding of periodic subset n capital Z, which satisfies.
Is phi just any function?
What?
What, phi?
Phi is some test function which here is quasi-periodic. For example, polynomial, trigonometric quasi-periodic polynomial. And here we have mean value over the m-dimensional unit cube, which is the periodicity cell for the matrix A and for the right side function F. And they everywhere transform capitals, small capitals into small letters to the capital letters. So I have here equation for periodic function. But what is here gradient with subscribe y? It is not full gradient. It is not full gradient over the m-dimensional variable z. We have here derivatives which can be called as some directional derivatives. They are calculated in the following form. So you have here the direction which is determined with the line from the frequency matrix. And the most interesting case in our considerations is the case when dimension d and m fulfill the following inequality, the restrict inequality. So we have here degenerate equation. It's quite non-trivial to obtain the solution, but really it is not real, very hard problem. We apply Galerkin method and existence of Galerkin approximation can be proved, and beforehand we establish the following a priori estimate for the solution of equation star. This is the following a priori estimate. Galerkin approximation surely satisfies this estimate, so this allows us to pass to the limit in the sequence of Galerkin approximations and to define the solution of the equation star as the limit of this approximation. But here we have norms of Sobolev spaces of periodic functions, which can be defined through the Fourier coefficients of the periodic functions. But what is about the regularity of potential of this potential vector? This is obtained through the following equation. Here we have tau and C0, the constants from frequency condition. So if the function f is sufficiently regular, so we have the arbitrary regularity of the potential n. And for sufficiently large S, we can succeed in necessary regularity of the solution of the equation 0. So I have commented what is the difficult moment in quasi-periodic setting, and now I also give here another lemma which is rather important in our technique. When we estimate the discrepancy of the first approximation in the initial equation, we make some transformations, and in these transformations the representations, the representation of solenoidal vector with zero mean value is very important. For a quasi-periodic setting, we state that solenoidal vector with zero mean value can be represented as the divergence with respect to variable y of some skew-symmetric matrix P, and there is hypoelliptic estimate for the periodic supports of these functions. And constant in this estimate depends on constants from frequency condition. That is all from divergent type equations, but we also studied non-divergent equations. They are of the following type. Here we have a highly oscillating matrix, symmetric matrix, which was defined previously. But if we have equation of this time, from the very beginning, it is not even evident why this equation is solvable, why this resolvent exists. So we will demand so-called Cardes conditions on the matrix A capital Z, and this condition will ensure existence of initial problem and homogenization result. I will formulate this Cardes condition a little bit later. So, in non-divergent setting, which we are considering now, very important is the so-called ground state equation. It is necessary to have the positive solution of this equation, which is not even positive, but is strictly bounded from below. And Cardes equation ensures to state that we have the solution of this ground state equation in quasi-periodic setting. Now, first of all, I must say that homogenization of non-divergent equations were studied more than 30 years ago by Zhikov and his pupil Serezhudinov. Here we have quite common result for the homogenization from the first glance, but in a non-self-adjoint setting, the procedure of finding of homogenized matrix is rather unusual. We have here formula which involves the solution of state ground equation, and that's all. Now, what concerns the operator type estimates in this setting. To obtain operator type estimate, we must modify slightly the homogenized equation. You see here constant matrix A0, but in the right side function there appears the weight function which depends on the small parameter epsilon. That's why we denote the solution of this homogenized problem with V epsilon. And maybe some strange theorem. You take the solution of the homogenized problem and obtain at once the first approximation, not only zero approximation. This function approximates solution of the initial problem together with gradient. As usual, an operator type estimates the majorante in left side of the estimate is the product of L2 norm of the right side function f, epsilon, and constant, which depends on the constants which are involved in our assumptions on matrix and frequency vectors. Now, here is Cardes equations. It is equations on the dispersion of eigenvalues of the matrix A. Maybe it is useful to say that this condition sometimes is called cone condition. Why? If you take x's lambda 1, lambda 2, lambda 3, for example, these are x's of eigenvalues. So if we take the x's when all the eigenvalues are equal to each other, so we have matrix A capital, which is diagonal and with the same element on the diagonal, then all this inequality will be satisfied. So we must take matrices satisfying Cardes conditions which are from some cone with this axis. Now, here some comments how to prove the last result. There is reducibility technique which was elaborated long ago, more than 30 years ago, in the papers of Sergei Kozlov and Vasily Zhikov. This reducibility technique allows us to get from non-divergent operator with symmetric matrix, divergent operator with non-symmetric matrix. I have enough time and I will maybe demonstrate the main trick in this reducibility technique. You have function P, which is the solution of the ground state equation. Multiply by this function from the left our operator. Then we can transform it in the following way. Let's check, is it correct? No, here is something. No, is it correct? Yes. Then we can see that this vector is just, this is the component of the vector, which is divergence of the product of matrix A and solution P. So due to the solution, we know that this vector is solenoidal, and from the view of this vector, we see that its mean value is 0. So we have formulated previously that there is representations of these solenoidal vectors in the form of divergence of some skew-symmetric matrix C. So our transformations can be continued, and we can write here instead of the second term divergence of matrix S, which is skew-symmetric. But due to skew symmetry of this matrix, we can rewrite this last term in form, because the other term, additional, will disappear because matrix S is skew-symmetric. So our final representation of this product will be of the following form. Here we have matrix A multiplied by P, and we must subtract matrix skew-symmetric matrix S. So we transformed our operator to divergent type operator. Here we have symmetric matrix, but after subtracting of skew-symmetric S matrix, we have matrix A tilde. And what concerns this matrix, we must notice the following remarkable property of it. It is divergent free. In this case, the homogenization, it is well known, gives the homogenized matrix, which is calculated as the mean value of this matrix. But in this case, we will come to the formula which was given below. So after transformations of our problem non-divergent to divergent, we can apply our traditional technique, so-called modified method of first approximation, and come to the operator type estimate, which was shown before, theorem 2. There is some another technical lemma, maybe I will not speak about it. It also demands that frequency condition should be fulfilled. So maybe I will end my talk. In the end, I will say that here I presented you the results which are published in the journal, Russian Journal of Mathematical Physics, volume 22, number 2, year 2015. So
Translate into English.
it is published at the very beginning in English only. That's all.
Thank you very much. Questions? Tanya?
Explain why this matrix A tilde is divergence free.
Matrix.
Just erase this
Yes.
from the blackboard.
Yes.
You make some transformations. The
Yes.
initial matrix A
I understand.
was
Yes,
arbitrary.
I will
with
restore.
eigenvalues,
I will restore. It
close
is of
to
the
each other.
following form. It
Yeah.
is of the following form.
Yes.
And
You can raise the word, maybe it's easier.
no, no, no,
Okay.
no. No. So it is true. So this is the vector G, which is formed from the solution of ground state equation. So divergence, and we have proved that, and we have chosen the matrix S to be the matrix potential of this solenoid order. So
this is
G
due to the
equals
choice
to
of
S.
S. Yes. And that is why you have zero character.
Yes.
Other questions? Valeria?